So, this is the continuation of the previous lecture. Here we want to actually show using Xilinx ISS simulator, we want to demonstrate. So, we want to consider one 4-bit ripple carry adder as the example here. So, we want to implement using Verilog-HDL. So, let us go to our Verilog block and we are going to implement this Verilog. So, let us open a project, I mean what we have discussed already. So, in this we will create a new project, and here the name of the project is, I will say, 4 ripple carry adder. Ripple carry adder, it is like a 4-bit ripple carry adder. So, this is my project name. Next, I will go to this Spartan device, and we are talking about the Spartan 6, okay, and this is a package we will be using, I have discussed, and you can take VHDL or Verilog, but we will be using Verilog. All other block keep it as it is. Then this is the description of the project, the summary. You can double check, because even though we are simulating here, that means in the simulation you can arbitrarily take any device, but we want to make sure that when you do hardware implementation, the device must match, device as well as the package, okay, and also the device family. Next, now the project is created. So, you can see this project is like an IC where we want to implement a 4-bit adder. So, in the 4-bit adder, if you go back to our presentation, so we need a vector data 4-bit A, 4-bit B, carry in scalar, sum vector 4-bit and carry out scalar. So, here let us now just a minute. So, if you right click new source, so we want to create a Verilog module and we call it as a RCA. So, RCA 4-bit ripple carry adder. So, this is a Verilog file name and it is different from the our location, the project name. Next, I am not specifying any input output. So, you can go ahead, and this is a .v file is created. Now, I want to zoom. So, I have discussed that the time scale here, it is just for simulation purpose. So, it is 1 nanosecond is the time. So, any unit of time if you provide, it will be just multiple of 20 nanosecond, 13 unit, that will be multiplied by 1 nanosecond. And these are all commented. So, you can remove this line, okay. So, you can remove this line, no issue. So, you can remove this line. Now, this is a 4-bit ripple carry adder. In this ripple carry adder, if you look at the port, that means if you go to our presentation, A, I am taking a 4-bit data input, B 4-bit data input, C in, C out, S. That means we are writing, we can sum, we can write sum like sum, then we can write C out, then we can write A, B, C in. So, this is the 4-bit ripple. The ripple carry adder has a 4-bit data input A and B, and sum will be 4-bit, carry out and carry in are scalar. Then we have to define the what are the input. So, our input is like initially we are defining the vector input, which is a 4-bit number, and those are A, B. The A and B both are 4-bit number. Another input is the scalar, we have to specify, which is nothing but our C in. Another, the output will be vector, output will be our sum, which will be sum, and then another output is our C out. Okay. So, this is a port declaration. We have declared which are input, output, they are vector and so on. Now, if you go to the diagram, you see there are some 3 internal C1, C2, C3. So, those things we will make as a wire. That means, we will make C1, C2, C3. That means, we will define wire like a C1, C2 and C3. There are 3 wire. Next, what we can see in the diagram, That means, if we look at the diagram, first full adder we will have a carry in input sum. That means, we have to go, that means, let us instantiate, that means, we have a full adder. Assuming that we will make a full adder block, full adder, then instant name maybe get 1. Now, inside the full adder we are assuming there will be a sum, full adder will have a sum, full adder will also have carry out C0, just to make it, you should not confuse. Then full adder will have a data A, data B, and full adder will also have carry in. We are writing in small. So here it is. So here you can write C out, C small. So this is for full adder carry in, carry out. Okay. Now this is the structure of the full adder, and we want to create a full adder circuit, and this we are making dot. That means, we are calling by name, not by sequence. So we are just making name. We will internally connect. This name must be consistent with the actual full adder that we are going to build. Now we want to connect the local variable here. That means, the local variable here. So local variable here. Local variable. So if you take the first gate, what is the sum out of the first full adder? If you go to the first full adder, the first full adder sum out is the S0. That means, it will be, we have already defined sum, that will be sum 0, because here we mention sum 0 is the LSB and sum 3 is the MSB, sum 0. What will be C out of this full adder? It will be the wire connection of C1. That means, let us copy C1. What will be that first data? It will be A0. That means, it will be A0 LSB. Then what will be the? It will be B0, and carry in will be same as the actual carry in, which is here. That means, we will mention this one as the carry in. So this is a local variable. Now we have made. Next, I will just copy paste this next line. Here we have to change the second gate, that means, second full adder. So the second full adder, naturally it will be the first is sum 1, this will be bit 1, and this will be, if you go to that block, you will find the second case, the carry in is the carry out of the first, and its carry out will be C2 in the wire. So that means, is carry in will be C1, which is the local variable, which is the wire variable, and its carry out will be C2. Okay. Then we will actually copy paste this and make. So G3, then we will make sum 2, this will be C3, this will be A2, this will be B2, this will be C2. Why C3? Because if you go to the diagram, C3 is the out and C2 is the in. C3 is the out and C2 is the in. Again I am copying here. So 4 full adder, they are connected in sequence. So it will be fourth one. The fourth one will be sum 3, that is the MSB. It will be the actual carry out, because this is the output of the fourth full adder will be the actual carry out, and this will be the third, that is the MSB, and this will be the C3. So now this circuit complete, but it is incomplete because it need a full adder. You see there are full adder, so you have to define. That means now we are going for a circuit and we have to keep the same name. That means we are creating a full adder, and this is a Verilog module. So full adder. Now we have created a full adder. Again we can remove this line, redundant line. So we have to make sure that we should name the same thing. We cannot change the name. That means we just copy paste this, and if we go here, we will use this S, not internal. So, we will remove this, we will use this C dot, we will remove this, then you will use this A, remove this, then we will use B, we will remove this, we will use C in, remove it. Now, these are the our name. So, name must be consistent. So, this is the name, we have to declare the port. So, here all are scalar. So, there is no problem. Input. So, input is what? A comma B comma C in, and what is the output? Output is S comma C out. So, name must be consistent. Now, we have to write the code. What is the full adder? Again, full adder consisting of two half adder. That means, if you go to our block, the next level, if you look at this diagram, that means half adder. So, this is a half adder and half adder will make. So, half adder input A and B are the input, output is I am taking some small s and small c, small s, small c, small a, small b. Okay. So, I am creating an half adder, that means half adder I am calling. Half adder, let us say we are using one instances where we are using sum, again I am using dot bracket, I will connect link with that, then C, the half adder C, then comma dot half adder A, you can say A local variable. So, it may be same, or I will just to avoid A1 dot, I will say dot B1. Okay. So, this will take half adder will have two input, two outputs. So, this is done. Now, you have to link. So, we will link with that. First half adder, if you check, if you go, the first adder half adder inputs are same as that AB. So, that means we will go AB. Inputs are AB, that means we will simply connect local variable A, local variable B. And first half adder, what is the carry in? Sorry, carry out. So, sum of this first half adder, that means there will be S, that means internal variable. So, this we call it as a S1, the sum of first, that is a wire connection, and C1 is the output. So, that means we have to define wire here, S1 comma C1. There will be C2, S2 may not be needed because sum will be the actual sum. So, that means it will be what? It will be C1 and this will be S1, the local variable. Next, we will copy paste, we will go next. Here, we will make G2. Now, if you go to the diagram, the second half adder input will be the sum 1 and the carry in. That means, input will be sum 1, which is the S1, one input. Another will be carry in, which will be the actual carry in. That means, this carry in should be actual carry in. Then, what are the output? The output will be, if you go output to the second will be the actual output. That means, this output will be actual sum. This output will be actual sum, and the carry we are mentioning 2, carry 2 output. Then, if we go further, the actual carry will be OR of this carry out, the carry out of the second half adder and first half adder. That means, we will use OR gate 3. Here we have to make sure we have to maintain the sequence. The output of the OR gate will be C out, then input to the OR gates are C1 comma C2. That is it. Now, this level module is implemented. Next, we have to create this half adder. That means, if you go inside, you will see there is a half adder also. So, now with this full adder, that means if we want to synthesize, let us say first block, that means because we have to go, actually I am coming from top to bottom, I should have gone from bottom to top, but that is okay. Now I want to create another module, or I can just create another module. You can click anywhere, new source. I am telling this is my half adder, it should be a Verilog module. Okay. So in the half adder, again I can remove this redundant part. What is there in the full adder? So if you go to full adder, the half adder consisting of SCA1B1, SCA1B1. So it has to be SCA1B1. So we have to make sure that we make it consistent. That means SC, that means this dot symbol, SCA1B1. Okay. And what is the input? The A1 comma B1, and what are the output? Is the S comma C. You may or may not give any space because it will be ignored. Now what is the half adder circuit? Again, if you go to half adder, you can see here half adder is nothing but XOR for the sum and AND for the carry. That means I can get XOR get 1, which will be my sum comma A1 comma B1 and and get 2, which will be my carry out. That means C comma A1 comma B1. So that is it. Looks like we are all set. Now let us try to first synthesize. So we will synthesize this. Yes, we will synthesize. Let us see, because okay. So there may be some port line, we have to check where it is. Half adder, line 4, module, N module, not defined. Oh, I made a mistake, so sorry. That was a typo. So now it is synthesized, and you see each block. So first I want to see the RTL block. That means you go to RTL block, view the RTL block. So this is a ripple carry adder, and if you go inside each block, that means if I again open RTL block, this is a 4-bit ripple carry adder. Go inside, you will have such full adder, then you have a half adder and so on. So it is actually designed. If you go further half adder, you will find that half adder consists of all these blocks. So that means we are all set. We have designed our half adder and all these RTLs are ready and it looks fine. Now you have to create a test signal. Now we are creating a test signal, so we have to test the circuit. So again you go to new source, then you go to a text fixture, and I create that test RCA. We want to test the RCA. There are many options. You can test separately half adder, full adder, RCA. So I have to test the full adder, 4-bit RCA. Now again there will be a lot of redundant line, so I can remove that. So now here this data, you have to define the data, and these are the standard, you can initialize A, B, etc. Now I want to create, that means I want to change carry in signal, I want to create like a clock. I want to define a clock for the carry. That means I will make an always block for the carry in. So, my carry in will be, that means after let us say 100 nanosecond 100 time unit, I want to toggle this C in. C in will be equal to C in. I want to toggle, and I want to change, that means my data, that means I also want to change. If you want to give more begin, that means this is one block, then another block I want to create 20 nanosecond duration. I want to check A data, that means my A, that means okay. So, here always fine, I want to initialize. So, initialize AB. Now, what I want to make after let us say 30 nanosecond 30 time unit, I want to change the data, that means I want to make A equal to, maybe I will take, because by default if you do not specify it will take decimal, it is a 4-bit data. So, you can use let us say 14 and B to be 10. Then after, okay. So, I may not change even B. After another let us say 40 nanosecond, I want to change B to be 20 and so on. So, let us check whether we are able to do it. So, in the test fixture, so we have to first check the behavioral model, behavior syntax. So, I think C in is not declared, C in, acha, we have changed the notation, it should be capital C in, sorry. So, you have to be very careful about the notation. Yes, now it is coming and we are ready to go for behavioral simulation. So, now we are trying to check that what happened here. So, let us say we want to check the simulation. So, you can see actually our carry signal, I mean if I specify, just a minute, I want to show. So, this is our carry in, and you can see I am changing the carry in periodically. Okay, as a result the sum must change. Okay. So, you can see initially I started with if I go all 0 0, the carry in was 0. So, sum was 0, everything was 0, there was no carry out. Now, at this time I have loaded with some value, that means I have changed my B to some 0 1 0, because 0 1 0 0, because what was the value I have inserted. If you go 0 1 0, that means I have loaded 14. So, if you take 14, so you can get the corresponding binary number. So, it is showing. As a result, the sum, what will be sum? The sum will be carry out is 1, sorry, your carry in is 0, B actually is changed to 0 1 0 0, and sorry, A has changed here. So, A has become 1 1 1 0, and since there is no carry in, B is 0. So, sum is same as carry that A. So, sum is equal to A, because B equal to 0, carry in equal to 0. At this time, if you see here, we have now inserted carry in, also we have changed the B. So, as a result, this value will be, what is A? 1 1 1 0 plus 0 1 0 0. So, sum will be 0 0 1 0 and there is a carry out. So, by that way you can check the logically whether it is correct or not. So, you can get the updated value. Now, since you are making 1 and 0, so accordingly carry in and carry out, so the sum will be computed. That means we are able to successfully implement our 4-bit ripple carry adder. and by that way, that means we have learned that how to we have learned how to simulate, and we have how to simulate behavioral simulation, how to check the timing diagram, and we can customize the timing, and we have checked the simulation waveform. By that way, you can check any logic. In fact, you can check your half adder circuit, you can check your full adder circuit, you can check the full ripple carry adder. So that means we have discussed. Let us start. We have already discussed that example of the 4-bit ripple carry adder. In summary, we have discussed the step for simulation using Xilinx ISC simulator, and we have also discussed example case study using Xilinx Webpack. I hope in the subsequent lecture, when you go to cube format and all, we will show some more case studies, and again the interested participant can check the simulation using Xilinx ISC tool, but again it is not mandatory for exam as well as assignment point of view, but it is important to know the Verilog coding, that will be part of the syllabus. That is it for today. Thank you very much.